Okay, so now we're going to talk about sleep deprivation and how our brain does the sleeps, what parts of the brain, how, etc. But I do want to take a moment just to talk about the relative um, propensity for individuals to develop sleep disorders, right? So, about 70 million Americans will have some level of a sleep related problem, with about 60% experiencing chronic sleep issues. Not enough people sleep full nights. So, over 30% of adults, over a third of adults in the United States report sleeping less than that 7 hour average. Remember, we need this. We need at least 7 for most people, but a lot of people say they don't sleep that much. And half of Americans do say they feel sleepy during the day between 3 to 7 days per week. Now, sometimes this is pathological, sometimes it's not. Sometimes it's from neurological conditions, sometimes it's from other health conditions, and sometimes it's just from not sleeping enough. There are a lot of reasons why someone may feel sleepy during the day, which is why we have to explore it when they do. So, some of the effects that we see when individuals experience deprivation from sleep actually can be quite interesting. And when individuals start to lose sleep, we see some pretty consistent effects on certain aspects of the individual. So, the 3 consistent effects that we tend to see upon deprivation of sleep is an increase in the feeling of being sleepy, which makes sense, a negative affect, so a bad mood. Puts people in a bad mood, and then it also makes them more irritable, more susceptible to feeling negatively, thus the negative affect. And then we also see poor performance on certain types of tests that require sustained attention. Okay, so your brain starts to take over and tell you that you need to sleep. It's distracted, you're irritable because you're tired. Absolutely, all of these things happen. When it comes to cognitive function, the results of studies have been somewhat variable, and it really depends on what specific aspects of cognitive function have been studied. So the most consistent data supports that there is an impact on an individual's executive functioning. So their ability to solve problems, to assimilate pieces of new information, to utilize and access their working memory, and to make decisions. All of those things appear to be impacted by sleep deprivation. We also see changes in the physical body as well as a result. So we see increases in blood pressure. We see changes in body temperature, usually a reduction, but we also see a reduction in immune function, and we see potential hormonal and metabolic changes. So there are certain hormones, certain parts of our body that actually fluctuate throughout the day in response to kind of a circadian cycle. So things like cortisol, our stress hormone, tends to have different levels during the morning versus the evening. We see different uses of insulin and the process of storing and releasing insulin, so gluconeogenesis and glycogenolysis. Those are tough words, but the storage and release of sugars in our bloodstream to use energy. So we do see these changes happen as a result of sleep deprivation. So we see negative mental as well as physical changes over time with sustained deprivation from sleep. We also see over time, and this doesn't take very long, it depends a little bit on the person, but we'll see people will start to engage in what we call microsleeps if they've had a significant enough sleep deprivation. And these microsleeps are considered very brief periods of sleep where the individual doesn't necessarily even realize that they've fallen asleep. So they may actually kind of continue doing like an automatic behavior. They may be sitting straight up. They might be standing. They may not even fully close their eyes. And they may kind of just be slow to respond, but they may have these brief moments. It almost looks like an absence seizure in a way, but very brief, where they sort of are asleep. They are EEG asleep, right? And of course, this can have negative impacts on things like their ability to remain vigilant. We also want to think about the interplay between sleep deprivation, and stress. So is the lack of sleep the thing that causes these issues, or is it the stress from not sleeping that's causing issues? And it's hard to know for sure. There have been some animal model studies. So as you can see here, this carousel apparatus. This was an experiment that looked at a sleep-deprived rat versus one that was a yoked control rat, so they didn't have as much stress of falling over essentially when they were sleeping on this rotating turntable, if you will. And by 12, I think on average, the rat that was stressed out by being sleep deprived would die much sooner than the rat that wasn't. But does this connect with stress? Is the stress of having to be awake, right? Because you kind of have to have a reason to stay awake, right? If you're relaxed, if nothing's going on, you're if you've ever watched a boring thing on a couch, right, you're much more likely to fall asleep than if you are driving in a snowstorm, right? If you're stressed, that keeps you awake too when you need to be. So it's difficult to know what kind of proportion of those two things play into each other. We also want to think about the effects of sleep deprivation on our types of sleep. So those slower wave sleeps and then our REM sleep. So you can see we'll see essentially what we call a REM rebound. So you can kind of make up sleep. You can't make up sleep in like the hour for hour sort of thing, but people who have experienced some sleep deprivation, we will have a higher efficiency in general with REM sleep. So they will initiate REM faster and have more of it essentially. But we also do see, again, antidepressants oftentimes will suppress REM sleep, but that doesn't seem to have a significant impact on things such as memory and attention. And when we see individuals wake up during REM sleep repeatedly, we don't see significant sleepiness throughout the day following that. If they stayed awake during REM periods, so they were woken up and stayed awake, they don't always have REM rebound. So it seems more it's like a holistic, you've lost sleep, not necessarily you've lost specifically REM sleep that causes this increase in efficiency of REM sleep. And then our slow wave sleep, we can see sleep deprivation in general will increase the efficiency of sleep itself. And there's a higher proportion of the sleep cycle following periods of deprivation. So people who sleep in kind of your average range that's 6 to 8 hours a night will experience a comparable time in that shorter wave sleep. But what we do see is if you repeatedly wake someone up during shortwave sleep, they will experience sleepiness the next day. So there are some differences in sleep deprivation and when interruptions in sleep occur and how people feel about it too. And REM is still quite an elusive experience. It doesn't seem to be required for sustained life, but when you have sleep deprivation, you're more likely to, your brain sort of seeks it out. So it's a very interesting thing to think about. So the other piece we want to talk about is the areas of the brain that sleep is associated with. And there's actually 4 primary areas that are connected with the functionality of sleep. So we have the hypothalamus, and then we have the reticular formation. And those are like our big pieces of the brain that connects to sleep really directly. So when it comes to the hypothalamus, we've got our anterior and our posterior hypothalamus. And the anterior hypothalamus is associated with promotion of sleep. So it promotes sleepiness, promotes falling asleep. Where a posterior hypothalamus is actually a wakefulness promoter. So it actually promotes individuals working or staying awake, essentially, right? So really interesting stuff. These two kind of work to balance each other out. So we always think about just feeling sleepy, but there's pieces of our brain and chemicals, hormones, et cetera, that actually make us feel more awake as well. Of course, we think of caffeine, but there's so many more things beyond caffeine. So there's pieces that turn on sleepiness and also turn on or turn off wakefulness. The other pieces are reticular formation. So we have our reticular formation as well as the caudal reticular formation, which is the reticular REM sleep nuclei. So the reticular formation is this red circle up here. Excuse me. And when the reticular formation is experiencing low levels of activity, that's associated with sleep. High levels is associated with wakefulness. Now, our caudal reticular formation is actually a number of different nuclei, so that's why they're called the reticular REM sleep nuclei. And what we'll actually see is the various pieces here that go through the brainstem will serve different types of functions. And it appears that REM sleep is controlled by a variety of different nuclei. It's not the one singular pathway that affects our sleep, particularly REM sleep here. So we can see is changes to these, the health, if you will, of these nuclei will cause changes in some of these aspects. So things like the respiratory changes that we talked about, muscle relaxation, eye movements, twitching, EEG waves. So the types of spikes and the hertz, the amplitude of the waves will actually potentially be disrupted or changed upon activation, dissection, damage to these various nuclei. So each site is actually responsible for a major function of REM. They don't all work singularly together. Very interesting stuff. These all sort of play a role in our wakefulness, our sleep, and our REM function. The other piece, of course, that should be discussed is the circadian rhythm, our circadian sleep cycles. So even without light cues, like I mentioned before, individuals, even for up to about a month or so, will maintain close to a 24-hour cycle of sleep-wake. I think it oftentimes will go out to about 25 and a half hours. So the circadian rhythm of an individual is actually a quite common thing. It's something that people have by and large, right? And there are actually a number of nuclei in the brain that are associated with maintenance, if you will, of our circadian sleep cycle. So the pieces that we see that are mechanistically associated with circadian rhythm is our suprachiasmatic nuclei, or SCN. But then we also have the retinohypothalamus tract within that, the superior cervical ganglion, and the subparaventricular zone, or the SPZ. So these all work as in that group called the suprachiasmatic nuclei. It's hard to say, but they all are receiving information or processing information through different pathways. So the retinohypothalamus is visual, the pineal gland is the superior cervical ganglion, and then the SPZ is more just associated with the sleep-wake rhythm, right? So it's not thermoregulatory, but it's that deep brain part that works on that rhythmic sleep and wake cycle, if you will. So these are pathways. The SCN is a cluster of neurons. It's in the anterior hypothalamus. And when we do see lesions in this, in the SCN, we will see changes in circadian rhythm. We can also see challenges in the circadian rhythm for people, say, who are fully blind, so cannot sense light and dark. They can have what's called non-24-hour sleep-wake disorder. We can give medications to help with that as well, but their sleep cycles can sometimes be a bit more challenging too. So in the retinohypothalamus tract, if we see lesions there, because this is the vision part, the visual stimulus of light and dark, that can affect the ability of an individual to synchronize to light-dark cycles. With the superior cervical ganglion, this actually directly innervates our pineal gland, and some of the hormones that are associated with sleep-wake are produced through there. Particularly notably is melatonin. So melatonin is a product that is released within our body to tell us that it's dark and it's time to sleep. It's a sleep-promoting neurotransmitter, right? And then we have our SPZ, which again is part of just regulation of the rhythm of day-night cycle. So the neurotransmitters that are involved in this are listed here. So we actually have stuff that makes us sleepy, So, and not all of these have medications associated with them, so we won't spend too much time on them in subsequent videos. But we have our sleep promoting products. So, probably the most common ones you'll run into are melatonin and GABA. And then our wakefulness promoting over there. Oop, my finger over there. So acetylcholine, dopamine, histamine. That's why antihistamines like Benadryl make people feel sleepy. We have orexin or hypocretin, norepinephrine, and serotonin. So all of these can be wakefulness promoting. And by blocking the activity, particularly in certain receptors, then we'll actually see more sleepiness. So histamine, for example, there are gastrointestinal stomach products that block certain types of histamine receptors, but are much less likely to cause you to feel sleepy versus certain types of antihistamines or older allergy medicines are much more likely to make you feel sleepy. We actually have products now that will turn off orexin as well. So we'll actually turn off our wakefulness promoting products too. So our next section is going to talk about insomnia. It's going to talk about treatment, etc. But this is where we're going to end this particular one.